So in 4.4, you can see uh, we'll try to graph functions where a couple of informations will be given. Okay, maybe the uh, interval of the increasing, interval of the decreasing, the critical points, mm, concavity, inflection point. These informations will be given. So from that, we want to graph the function. Okay, so let's see how can we do that. Okay, so we'll come back to this, um, but before we want to see one example. Okay, yeah, like this one. Then we'll come back to this uh, guidelines. But let me first show uh, what are the things we could expect and how can we exploit those situations to craft uh, um, you know a couple of really interesting functions. So first of all, um, if we know that the first derivative is decreasing, let's say at a point 0, okay? Let's say at a point 0, our function was decreasing, and after, I shouldn't say at a point 0, before the point 0, the function was decreasing, the first derivative was decreasing, and after 0, the function starts to increase, okay? So if you just consider the point 0, can you imagine what should happen there? If you remember, we know that if a point has decreasing first derivative before it exists, and afterwards if it starts to increase, you know from one of the previous theorems we know that at 0 we expect that the function will have a local minimum, right? We know that we have seen this theorem before when we were working on min and max, I guess in 4.1 or 3.11, somewhere uh, either in 3.11 or 4.1. So and if you have attended the lecture or seen the videos, you have already seen the theorem, right? So we expect a local minimum there. Okay, now if you have more than one intervals like, or rather points like this, where you have change of directions, then what should you do? So we just need to plug in each information separately and join those. So for example, if I now consider 1, let's just say I have a point where before that point my function was concave up. Now if you remember what's concave up, that means um, if you draw a tangent line at those points, or okay, let me ask you this way. Can anyone tell me how to identify if a function is concave up at a point, or at a certain interval? How to identify that graphically? Anyone? Because these informations will be needed. We need to know the basic criteria, basic requirements. It's easy to understand how it's decreasing or increasing, but what should we do for concave up or concave down? Anyone? We have seen this before, right? Just give it a try, even though it's wrong. No worries.
Don't we look at the second derivative of the problem?
So the second derivative, so how to do that on graph? If a function is given,
Oh,
I can understand, but how to do that on a graph?
just by like looking at it is what you're asking right now?
Yeah, I mean, if you can just eyeball a graph, you don't have anything else, you still need to say that whether it's concave up or down. How can you do that?
Based off the curve.
Okay, so based on the curve, what should we expect if we are trying to say that it's concave up?
Like kind of an open, half open U shape. I don't know what to call it.
Yeah, okay, good try. Anyone else? Okay, so if you are given a graph, all you need to do, so let's say we are trying to find what's happening before and after this point one, okay? So what we'll do, we'll start uh, before this point one and see how the tangent is behaving and check the behavior of tangent afterwards as well. So if it's concave up, that means your uh, derivatives will be on the rise, okay? And if it's concave down, then it will, or rather, or I might say the best way to see is if you can find a point where the concavity gets zero. I mean, I should say the first derivative gets zero. If you can find a point like this, then you will see before that point and after the point, the derivatives will change. For example, let me show this one. Not this one. Where is that graph? I have a really good graph for it. If you remember, I did show one last time. Hopefully, yeah, there you go. This is the best graph you can imagine. If you can remember this scenario, then it's really easy to imagine if the information is given. I mean, for a graph, when you are trying to graph a function, the information will be given, right? Nothing else will be given. So the most important thing is to visualize it in your head. So what happens when we say it's concave up? Let's see that. So as I said, all you need to find is to see if there is a point when the first derivative is zero. If you can find that, then it's really easy to see where it's concave up. So for example, at this particular point, whatever it is, I know it's pi over 2, but let's say you don't know. At this point, you can see there is a parallel tangent line, right? That means the tangent is zero. The slope of the tangent is zero. So for concave up, all you need to remember that your slope of the tangent will get increased as you move to your right. That means, oops, someone in the waiting room. Give me a second. Okay. That means if you're moving to your right on the real axis, real number line, so that means if you start from here and go to your right, your slope of the tangent will also increase. So if you consider this particular point, we know at this point it's zero because we have a parallel line. We can imagine a line, even though it was not given. We can clearly imagine a parallel line, excuse me, to the x-axis at this point, right? So just before this point, if you draw a tangent line, you can see it's negative. Just after this point, if you draw a tangent line, you will see the slope of the tangent will be positive. That means from negative to 0 to positive. So as you are moving to your right, the slope of the tangent is slowly and slowly getting increased, right? And same goes for the concave down. I mean, not same, the opposite direction. So we can imagine a parallel line here, even though it was not drawn, we can imagine, because it's the maximum point, right? So at the maximum or at the minimum point, if it's not the boundary point, we expect a parallel line to the x-axis, right? That's why the first derivative is 0. So if we draw tangent lines here, these will be positives. Here it will be 0, and afterwards it will be negative. That means you can clearly imagine that it is slowly and slowly getting decreased. Okay, the slope of the tangent is decreasing as you are moving to your right. So if that's the case, that means if you can draw a slope at a point, and as you move to your right, if you see the slope is actually getting increased, then you say that it's concave up. So that means you might have these two cases. Let me show this as well. Yeah, this one. These two. I wish I could show this together, but let me give you a reminder. So, for example, you can see if you draw tangent lines here, okay, it will be positive, right? Then if you draw a tangent line here, it will be 0, and then it will be positive here again. So what does this mean? So at this point, your derivative is 0. It was positive here. So how can you reach from a positive value to 0? Definitely, if it's only possible if your slope of the tangent is getting decreased, right? You cannot reach from, say, positive 3 to 0 unless you slowly and slowly get lower values. Can you feel this? Just take your time, okay? Because graphing a function with these informations will be really interesting. But as long as you actually know what does this mean, try to imagine, okay? Try to digest all this, not really memorize this. Memorizing won't really help. So my question again, you have a positive slope here, right? Do you agree with that? At this part of the graph, you have a positive slope. Do you agree? Is there anyone who doesn't agree?
I agree.
And from a positive value, whatever it is, you are getting a 0 because you can, if you draw a tangent line here, definitely it will be parallel to the x-axis, right? So how can you go from a positive value to 0? Isn't it only possible only if and only if your value gets lower and lower as you move to your right? Do you agree? Okay. Now, as you are moving to your right, if you agree that your value is slowly and slowly getting decreased because it was positive here and 0 here, that's the definition of concave down, isn't it? So if you consider this point C, before this, it was concave down because even though it was positive, it was slowly and slowly getting decreased. Otherwise, it can't be 0 somewhere. all of a sudden. So if your first derivative, the slope of the tangent, in other words, is getting decreased as you're moving to your right, then we know it's concave down. Do you agree? And same goes for this part of the graph as well. So it was 0 here, and if you start drawing tangents, you will see a positive slope here. So from 0, it is going to positive values. Definitely, if you are moving to your right, your value or your slope of the tangent is getting increased, right? You're going from 0 to a positive value, whatever it is. It's only possible if the value is getting increased, right? So it's concave up for this part. And you can use this imagination, or rather, I shouldn't say imagination here because you can see this, but when the graph is not given, or when you are required to draw the graph, you can imagine this scenario, okay? Is there any other examples? Yeah, I think you can always come back to these graphs. Just remember, it's 4.3, slide 24, 25, or the entire slide, I would say. Yeah, 26, 27. These are good examples as well. Yeah, let me uh, ask you, why do you think this part of the graph is concave up? Anyone? Can anyone explain?
Increasing?
What increasing? I mean,
Oh, that's the original. I thought it was like a derivative graph. Never mind.
yeah, it's the original curve for y equals f of t, whatever the function is, doesn't matter. But they're saying, obviously we trust them, they're saying that it's concave up for this part of the graph. But why do you think it should be concave up? What are the characteristics you can locate here which can convince you that, yeah, it should be concave up? Anyone? Just give it a try using the definition, you know. Yeah, go for it.
It shows t increasing and it's f of t.
So in this case also the t is increasing, but it's still saying concave down. Now, what can I tell about it?
The rate of change is decreasing.
How do you think it's decreasing? I mean, let's say I don't really know anything. I just only know the definition that uh, if the slope of the tangent is decreasing as you are moving to your right, that means as you're increasing the values of t here, your slope of the tangent is decreasing. I just only know this definition of concave down. So can you convince me that, yeah, it is actually concave down? If all of you can convince me that this is concave down and this is concave up, even though both the functions are increasing, then you are all set to use these informations in 4.4. But if you still have doubts, we want to clarify this first. Otherwise, it would be difficult to draw these graphs, okay? Is there anyone who is confused or uh, who can convince me? I mean, let me try both ways. If you're confused, let me know. If you can convince me, let me know as well. You'll need this, you know, complete, clear understanding, you know, of this to draw graphs using the information you'll have rather. So is there anyone who can try to convince me why it's concave up and why it's concave down, even though both are increasing. Both functions are increasing. Anyone, just give it a try. If you try, even though you don't think it's good enough or convincing enough, if you try, you will see uh, the things you need to know, which will actually help the cause, okay, to clarify your concept. No one at all? Okay, let me try and convince you again. So let's forget about this side note. Just try to use our um, concept here. So at this point somewhere, I can imagine a tangent parallel to the t-axis. Do you agree? Even I think at this point, if you draw a tangent line, it will be close to parallel uh, to the t-axis. Is it involving mean and max? Not always. In some cases, it will involve mean and max. Okay, so I can imagine it's somewhere here, maybe at this very point, if I draw a tangent line, it will be parallel to the t-axis. Do you agree with that? Do you agree? Or can you actually see this? At least you can see that it's pretty close to being parallel to the t-axis, right? And if you move forward, you can see the tangents, the slope of the tangents are getting bigger. Don't just trust me. If you can draw a line uh, on your scratch paper, if you have any in front of you, just draw a curve like this and try to draw tangent at some of these points. Move to your right, go to your right, increase your value of t, and at the corresponding values on the graph, try to draw tangent lines. You will see it will increase as you move to your right, like this. Do you agree? Don't just trust me. If you're confused, let me know, as I said. If you're confused and if you don't let me know, I won't be able to help you, right? Let's try this one. So looks like at somewhere here there is a line. If you draw, if you draw a tangent line, it will be parallel to the t-axis, right? Somewhere here. And if you start imagining from here, if you start drawing tangent lines, you'll see it will slowly and slowly, the slope slowly and slowly will get decreased. Can you see the lines? Imagine a line I'm drawing here, starting from here. This line will go like this will go like this. You can see the slope of the tangent is slowly and slowly getting decreased. Do you agree? And that's the definition of concave down. Any question from this? I know we are reviewing this stuff, but I could see some of you are still, some of you who still have doubts uh, on the graphical representation of concavity. No questions at all? All good? Okay, let's go back to 4.4 and see if we can use these informations to draw the graph. Okay. All right. So for this part of the graph, you can see if I start drawing tangent lines here, right? it's actually getting increased as I'm moving to my right. So it's concave up. And for this part of the graph, if I go to my right, I can see the slope is slowly and slowly getting decreased. So it's concave down. And it will be actually, or rather, will be doing this in the opposite order. That means concave up will be said, will be using this information to draw the graph. Now if I say that from negative infinity to 0, our first derivative is negative, and it's concave up in that interval. Then from 0 to 1, our first derivative is increasing, and it's still concave up in that interval. And at 1, we have an inflection point, and from 1 to 2, our first derivative is still increasing, but now it's concave down. Then can we draw this graph? That's the question. If yes, how? So first of all, from negative infinity to infinity, our information said that the first derivative is decreasing. Then from 0 to 1, it said the first derivative is increasing. So I expect at 0, we have a local minimum. Or rather, we expect, right? So we can imagine that there should be a bowl-like shape here. Okay? We can just start, it may not be the right thing, but we can start imagining this, and then we'll combine all of this to get our final result, right? Okay, then again, from 1 to 2, our first derivative is still increasing, but we have said that it goes from concave up to concave down. So that means at 1, we have an inflection point. Okay, so that means if the function or if the slope of the tangent was increasing at this point, it will be decreasing on this part of the graph. So that means it will be 0 somewhere here, right? So if we join this, we'll get a shape like this. A half S or horizontal S, something like that. And if you're able to just understand up to this, bingo, you're done. Because for finding these graphs, spatially in your homeworks, that couple of options will be given. Okay, so if you can understand this, that the graph looks like this horizontal S or something like that, you'll see you will have one option like that. There can't be two options using this same information, which is true. Using this information, there you can only draw one precise graph. You can't really imagine any other things. It can't be this way, right? So we'll be using this to draw graphs, but before that, again, let's see the guidelines, and we'll come back to it. Okay, any questions up to this? Anything that's confusing? Maybe it's the first time you're seeing this, so if it's not making too much sense, no worries. We'll practice a lot of this, okay, on this discussion, on the homeworks, and of course before exam you'll practice a couple of from the worked out problems or even from the exercise, right? So slowly and hopefully it will make more sense. No questions at all? Okay, let's see the guidelines. So the first one says, identify the domain or the interval of interest. Now, let us quickly, really quick, go back to the definition of domain. Can anyone tell me the definition of domain? Although we haven't really gone deep into the concept of domain on this particular course, because we have seen this before in the pre-calc or even in the algebra class, I guess. Definitely in the pre-calc. So what's the definition of domain?
Isn't it the area between 2 points?
Not really. Anyone else?
The domain is the range of x values you can have.
Range of x values for what? Yeah, you're almost right, but just
In the interval
um
slash that will put out a y value in a function.
yeah, I can see what you're trying to say. Yeah, so the thing is, the domain is the x values for which your graph, or I should say function, your function will have a defined value. Okay, it is the x values for which your function will have a defined value. Let me quickly show one example. Not this one. Okay, yeah, let me just quickly show you the domain from this graph. So from negative infinity to -1, we have a defined value. Obviously the -1 is not included, so you can't really have brackets there. You can only have parentheses. So from negative infinity to -1, you have a defined value. Then at -1, you don't have a defined value of the function. Then again, from -1 to 0, or I should say, yeah, -1 to 1, again, in parentheses, that means both sides open, -1 and 1 not included. Again, you have a defined value. And at +1, you don't have a defined value. And then from +1 to positive infinity, you have a defined value. So that means your domain is negative infinity to -1, both sides open, then -1 to 1, both sides open, then 1 to positive infinity, both sides open. Or in other words, if you try to simplify it more, you could say the domain for this function is every real number apart from -1 and 1. Or other than -1 and 1, any values, any real values will be a part of our domain. Only -1 and +1 will not be a part of our domain, because you can see there is no defined value at +1 and at -1. So this is the domain. That means you need to have a defined value for that particular function, whatever it is. Okay, so one of the most important things is to understand your domain, or it said interval of interest. Now what does that mean? So that means your questionnaire will actually give you a certain interval. You don't need to imagine anything beyond that interval. or beyond those intervals, I might say. You might be given 2 or 3 intervals, and you just need to use the next couple of informations, whatever you have, in those intervals, not beyond that. Okay. All right. Next, exploit the symmetry. Now, what is a symmetry? I think I briefly explained this a couple of days back. That is, if you can draw a line, or if you can imagine a line, you don't need to draw a line. If you can imagine a line, or for your convenience, just for a couple of seconds, if you can draw a line, and on both sides of that line, if you can see the graph is behaving same, or have the same behavioral aspects, that means it's going in the same way on both sides of that line, then from the graphical representation of that, we say we have a symmetry. For example, I hope I can find one real quick. Yeah, I think, yeah, this one is a good one. So if you can imagine this line, you can see on our left, the graph is behaving like this, and on our right, the graph is behaving like this. So it's behaving almost the same, but it's not exactly the way it behaved on our left. If it behaved like this, if it had created a shape, M-like shape, then on our left and on our right, we would have had the same looking graphs, like. So we would have said that it's a symmetry. Can you imagine? Just imagine this graph, instead of going to downwards, if it was like this, same way as this, right? We would have said this line is creating a symmetry. So how can you use that? So if you have a function, you can actually check whether it's even or odd, or it might be said that it's an even function, or it's an odd function. Now, how can you use that? So first of all, let us quickly go back to the definition of even and odd function. If you plug in a negative value of x, and if you still get the positive, the main function in return without the change of sign, even though you have changed the value of x to negative x, still you get the same function in return, then we call it an even function. And if you just change the value and get the negative function in return, then you call it an odd function. Let me quickly tell you one example each. So let's imagine f of x equals x squared. Okay, your function, let's imagine it's x squared. So if you plug in negative x in place of x you have for the function, can you see what you are getting in return? You're still getting positive x squared. Do you agree? Do you agree? Let me start showing the screen. Hopefully this will be more convenient for you guys to understand. So what I want you to do is to have this slide open in front of you, and meanwhile keep an eye on the screen I'm sharing as well. Okay. Okay. Can you see the screen I'm sharing? Today is 21. So have that slide open because you'll need this. And you just need to cross check it with the screen I'm sharing, okay? So if you have f of x equals x squared, if I plug in negative x, let's see what happens. I'll replace my x's with negative x, and negative x, the quantity squared, is still x squared. Do you agree? And f of x, x squared is actually f of x, right? So from negative x, we are actually getting the same function in return. So we call it an even function. Any question from this? I guess most of you have already seen this. Still, if you have any question, just let me know. Now let's see what happens for an odd function. So if we replace x for, or rather by negative x in the function x cubed, since it's an odd exponent, we'll definitely have a negative in front, right? And I can write it as negative times x cubed. I'm just trying to show how it's done. And this guy is actually just f of x. So we started from, I'm doing this again. From this, f of negative x is actually giving us negative f of x. We call it as an odd function. We define it as odd function. Any question from this? No questions at all? Okay. So if this information is given, whether it's odd or even, then it's really an advantage for us. How? So if we know that even if we change the values to negative, we'll still get the same function, or in other words, if we know the function is even, then actually it helps us to imagine that this is the positive values of x, right? And this is the negative values of x. So we can imagine that the function will behave similarly on both sides of 0, because we know the function is even. That means for negative x, we actually have the same behavior. So for example, if we just draw this graph, I'm just showing one example, okay, how to use this, how to exploit this. So for negative x, it will also have x squared, right? Sorry, my iPad is creating some problems. Sorry about that. Okay. So that means if we have just a couple of values on our right, if we know and plug in, let's say, a couple of values and know that the graph is going like this, straight away, without doing any further calculation for any negative x values, we can just use this as a mirror. Okay, let's imagine we have a mirror here, and just copy this part here. That's it. It's slightly bigger than I wanted to do. Okay, yeah. So that means if we have a mirror here, these will be mirror image of each other. It's the symmetry we are talking about. Okay, so we can use this information. So we'll see more examples of it. Okay, how to use this symmetry. Okay, the next thing is, if you can eyeball the slide, it says number 3, find the first and second derivatives. So using the first and second derivatives, we know we can derive lots of informations. You know, the extreme values, obviously concavity, inflection points, critical points, intervals of increase, intervals of decrease, right? We can actually determine a lot of things from these derivatives, first and second derivatives. Okay, and we'll be using this, and we have seen one example of this, that how to use this first and second derivatives to graph a function, right? We'll see more examples soon. Next one says find critical points and possible inflection points. Okay, obviously, if we know that we have a critical point somewhere or an inflection point somewhere, it definitely gives us a head start, because we know that we can start from there if we know how to deal with the critical points and inflection points, right? Using the definition. So inflection point is the point where your concavity changes. That means from concave down, it goes to concave up, or vice versa. And for the critical points, we know that either there will be a minimum or maximum value at that point, or the first derivative will not exist at that point. That means there will be a corner point, or in other words, if we draw a tangent line there, it will be vertical to the x-axis. We know the definition, so we can use this. Next, find the intervals on which the function is increasing or decreasing. Obviously, for a certain interval, if it's increasing, we know how it's behaving. We can't really conclude, because if you remember, increasing doesn't mean that it goes like this. It even might go like this, right? So at least first of all, we need to identify, or we need to know whether it's increasing or not. If it's increasing, then we need to know whether it's concave up or down. So for this one, it's concave up. For this one, it's concave down. We know the shapes, how it behaves, right? Even though on both occasions, it's increasing. So first of all, we want to know whether it's increasing or not. Then we want to know whether it's concave up or down. If we know these two informations, we can clearly imagine how will it behave. Do you agree? Right? Okay. Now, the good thing is, though, if the function itself is given, if somehow, let's say, I give you the function, then it's even better, right? If the function is given, I can actually calculate this. I can find the derivatives. I can set this to 0 and solve it for x. I can set, or rather, I myself can calculate the intervals of increasing the concavity and find all of this, right? I have shown you one example how to do this for a function, where is that? Yeah, here we go for this one. If a function is given, you can actually find the critical points, the intervals where it's increasing, the intervals where it's decreasing, the interval where it's concave up, the interval where it's concave down, the inflection points, all of this, you can easily calculate it. So if the function is given, it's even better. But not always the function will be given. Instead, in some occasions, only the informations will be given that, hey, for your function, whatever it is, in this interval, let's say from A to B, it will be increasing but concave down. For example, I'm just setting up an example. Not always the function will be given, but in some cases, the function will be given. And from that function, you can actually derive these informations. If the function is not given, then the informations will be given. You don't need to calculate that. It can't be both, it will be either of this. Either the function will be given or the informations will be given. Either way, eventually we'll need these informations to draw the graph. Okay, now, next, we need to identify the extreme values and the inflection points, if there is any. So if we can calculate the first and second derivatives, obviously we can locate the extreme values and the inflection points, if any, right? We know how to do that. We have seen this before. But are we done? No. We may need to see a couple of more things. One of the things would be to see the asymptotes, if we have any asymptote. That means if there is any line which our graph will not cross, neither touch nor cross it, if there is any point like this. So if the information is given that, hey, at x equals, let's say x equals a, you have an asymptote, you have a vertical asymptote. That means if you have a graph, obviously at a, you can imagine a line like this, right? But if the function is given, then you actually need to calculate it, whether we have an asymptote or not. And we know how to calculate or how to find the asymptote, right? If we have a fraction, we just need to see where does the denominator become 0. At those values, we'll have a vertical asymptote, right? Okay, and we can use the concept of asymptotes to see other asymptotes as well. If the function is given, it will not be a problem. We'll see examples of it, hopefully. Next, we need to see the intercepts. If the function is given, it's really easy to locate the intercepts. If we set the function to 0, whatever we have for x, I mean, if we solve it for x, these will be y-intercepts. Sorry, I shouldn't say y-intercept, it should be x-intercepts, right? Functional value is 0, that means y is 0, yeah. This is x-intercepts. And if you just set x equals 0, and then whatever you get for that function, then it will be y-intercept. For example, if you have, let's say, f of x equals 2x plus 3. So if you set this to 0 and solve it, 2x plus 3 equals 0. So if we solve it for x, you'll have negative 3 halves So this will be your x-intercept. And if you said x equals 0, it means f of 0, which is 2 times 0 plus 3, this will be your y-intercept. Okay? And knowing these points will be really helpful because we will know where it will cross the axis, right? Okay, and yeah, that's it. If we can combine these ideas, we can actually draw graphs. Or if we are given multiple choices, we can actually pick one which actually which fits the data best, fits the information best. We can actually pick that from the given information. We have or whether we have or we have derived from the function. So any questions so far? Although we haven't seen a graph combining all these guidelines together, but any questions so far from the definitions or the guidelines? Any question? I can't see anything in the chat, so hopefully you don't have any question. Okay, if you don't have any question, I think we are already past, yeah, it's already 10:13. Anyway, let's take a 5 minutes break to refresh our minds, and then we'll see a real example where we'll be using these informations and we'll try to draw a graph. Okay, so see you in 5 minutes. Let's meet at 10:19. Okay, all right. Who wants to tell me the solution for the second derivative? What do you get for this x?
I didn't get far enough to get all the x values, but I did get it simplified, if I could tell you that.
Okay, is there anyone who has these values of x? No one? Really? You didn't have enough time to solve it for x?
Yes.
Okay, what's the value? Do you have the value or you just?
Yeah, I did not write the value when the break home when the breakup room expired.
I didn't understand. Did you calculate the value?
Yeah, I didn't calculate the value when the breakup room expired. I don't have enough time to calculate the value.
8 minutes was not enough, really? That's strange. Anyway,
The problem is that I have a problem hearing you from where I am, so I didn't get the when you asked us to ask question. I wanted to ask question before the breakout room, before you put us in the break room. So when I was calculating it, I was on the verge of getting the x value when the break room expired. That's why.
okay. Anyway, so the thing is,
Are you?
Yeah.
So for the X values, is just where you gave that negative square root of 3 minus 1 and then 1 and square root of 3 that you wanted to see what we got when we plug those in?
No. I did say you need to solve this one for x, the second derivative.
Oh, okay. Yeah.
So if you solve this for x, this will be your homework assignment. After we finish, I want you guys to solve it. I don't know why 8 minutes was not enough. It should have been enough anyway. So no worries, you can still solve it after we finish. And then all you need to do is to check where this is concave up and where this is concave down. Okay, so now did anyone do this part? I mean, where it's increasing and where it's decreasing, in which interval?
Yeah, I did.
Okay, what did you get?
I got it's increasing over negative infinity to negative root 3,
Okay,
and then root 3 to infinity.
okay, and decreasing everywhere else?
Yeah.
Okay, did someone else get the same as him? Is there anyone else who has a different result other than this? So all of you agree with this? That means it's increasing in this interval from negative infinity to negative square root of 3 and positive square root of 3 to infinity. And in the other 3 intervals, it's actually decreasing. Okay, let's just agree with Matthew. Okay, now let's try to draw this graph. Okay. So first of all, I know that I have a vertical asymptote. I think I have more than one vertical asymptotes. Yeah, at -1 and at +1, right? Let's do this. So this is my -1, this is my +1, and I have vertical asymptotes here. So that means I can do this, right? So these are my vertical asymptotes at -1 and +1. Okay, now next we have increasing from negative infinity to negative square root of 3. Let's just first find out where the negative square root of 3 would be. So if that's 1, that would be 2. And we know square root of 3 is 1.7320. So that means it's somewhere here, right? It's somewhere here. And for positive square root of 3, again, if it's 1, it should be 2. And square root of 3 should be somewhere here, right? Okay. And from negative infinity to negative square root of 3, I know the function is increasing. Okay, so that is negative square root of 3, and up to this the function is increasing. Now how should we draw this? So before doing this, I want you to take you back to the main function to show you that can we have any other type of asymptotes here? Can you imagine any other type of asymptote here? And the answer is yes. Since
Yes.
okay, since the exponent in the numerator, or I shouldn't say exponent, the degree, that means the highest exponent in the numerator is bigger than the highest exponent in the denominator, what can we conclude? Do you remember?
Should it have a slant asymptote?
Very good. We have a slant asymptote. And how to find the slant asymptote? Let me give you a quick reminder. You just need to find the quotient for this. So our function is 10x cubed over what? Over x squared minus 1. So you just need to divide this. Oops, sorry. We just need to divide this and find the quotient. So if we can divide this, we get 10x, right? Because 10x times x squared would be 10x cubed, and this would give us a minus 10. So it would be positive 10 as the remainder, but the quotient will be 10x, right? Just simply divide it and find the quotient. So at y equals 10x, we have a slant asymptote. So we just need to draw it here. So that's y equals 10x. Oh, I shouldn't use this. Instead, I should use this. That's the slant asymptote, okay? And now I can draw the graph. I know up to negative square root of 3, it's increasing. So that's negative square root of 3. So it should behave like this. Oops, sorry. Yeah, like this. And then it starts to decrease. So it will go like this because of the asymptote, right? Because we have an asymptote here. Then we know for all this part it's decreasing. And when you will solve the second derivative, we'll see we'll have an inflection point here at x equals 0. It will behave like this. I'm leaving it for you. And again, we know from positive infinity to from 1 to positive infinity, a positive square root of 3, it's decreasing. So that's my 1. That's positive square root of 3. It's decreasing, so it will behave like this. And from positive square root of 3 to infinity, it's increasing. So it will go like this. Now you might be wondering, how did I get this part this easily? And I'll take you back to this because this is an odd function. So since we have this part, this will behave exactly like that, but in the opposite order. Okay, I think we are running short of time. So we'll start from here the next time when we meet tomorrow. But before that, your pre-class assignment would be to find this x values. Just set the second derivative to 0 and solve it for x. And subdivide the intervals using these x values like the way I have done here. Is the question clear? That's the first thing. I guess somehow, for some reasons, the question was not clear when I created the breakout room. I take the blame. Maybe I didn't say it properly. But is the question clear for tomorrow?
Yeah, could you scroll back up so I can see the equation again? I think I wrote it down wrong.
Yeah, there you go. So note this down. Your pre-class assignment would be to solve the second derivative, find the x values, and subdivide the intervals using these x values like the way we have done here. Okay. And we'll start from this graph, this particular graph tomorrow. I wish I had at least 5 to 10 more minutes, but I know some of you will go for work and 1 or 2 of you have some other class as well. So I won't really hold you back, but no worries. We'll start from here and we'll probably see 1 or 2 more graphs tomorrow.
Mr. Ike, I would like to see you.
Okay, just wait in the meeting room. Let's just wait for others to leave the meeting.
Okay, so what I wanted to ask actually on the lesson today is that the second derivative is the assignment for tomorrow.
Yeah, the second derivative. Solve the second derivative for x. Yeah.
So we don't need to like take the derivative again. We're just solving for x.
Right. Yeah. Excuse me. You already have
Okay,
the second
awesome. Thank
derivative.
you.
You just need to solve it for x.